Okay, so hello. So, continuing with the yesterday's session, I'll be discussing some more questions from the coordination chemistry chapter. Okay, so this is another question. The complexes of cobalt 1,2-diaminopropane 2 Cl2 plus and cobalt 1,3-diaminopropane 2 Cl2 plus represent an example. So these are the examples of the isomerism. Isomerism topic is also important from this chapter. Okay, so ligand isomerism, linkage isomerism, ionization isomerism, coordination isomerism. So these two complexes, the cobalt 1,2 and cobalt 1,3, these are examples of ligand isomerism. Okay, as you can see the structure which I've shown here, that 1,2-diaminopropane, this is 1, okay, this is 2, 1, 2, diamino, two amine groups, propane, 3 carbons, okay, so this is 1,2-diaminopropane, which is this, and this one, 1,3-diaminopropane, this is 1, 2, and 3, okay. 1,3-diaminopropane. So this is an example of ligand isomerism, where the attachments, although the coordination will be from this nitrogen only, nitrogen having lone pairs, and this is also having lone pairs. Similarly here also, but the structure of the ligand, the attachments of the ligand is different. So that is why it is an example of ligand isomerism. Okay. So this is the question, ligand isomerism. This is the correct answer. A. Okay, now, yeah, this is a very important question. You can see now. Okay, see, consider the two redox pairs. So this question is from the outer sphere inner sphere mechanism, and this is very important for both the exams. Okay, so two redox pairs have been given here: chromium 2, ruthenium 3, iron, ruthenium, osmium. It belongs to this group, and this is chromium 2, cobalt 3. Okay, I'm sorry. The rate of acceleration in going from outer sphere to an inner sphere mechanism is lower in 1 relative to 2. Its correct explanation is, okay, the rate is lower for this one, first one, as compared to the second one. So we have to explain the reason why it is happening like this. So these are some of the reasons that are given, that homo, lumo, or sigma star, or sigma star or pi star, pi star or pi star and sigma star. So you have to see how it is happening. So if we see that outer sphere mechanism involves pi star to pi star transition, that is from T2G to T2G. A complex having T2G, the electrons transferred from T2G to another complex having a T2G electron transfer. Okay, so there is no bridging ligand. This is very important. However, exceptions are also there, but that is not required here. So you can see that there is no bridging ligand involved for the outer sphere, and the complex can be inert or labile. So what do you mean by inert and labile? So basically, a complex is said to be inert when it doesn't exchange its ligands easily. It will not exchange, or it will exchange very slowly. The rate will be very slow, while for the labile, the exchange is very fast. For the ligands, exchange of the ligands is fast. So that is how the complex becomes labile. So in the inner sphere mechanism, a bridging ligand is involved. A bridging ligand is involved. You can see here. Here there is no bridging ligand, but the inner sphere there is a bridging ligand. So here the reductant is labile, while the oxidant is inert for the inner sphere. So reductant is reducing agent and oxidant is your oxidizing agent, right? So electron transfer occurs from sigma star to sigma star for the inner sphere, Eg to Eg. You can see Eg of one complex to Eg of another complex. Okay, now you can see, yeah, this is important. You can see that for the first complex, this is a complex consisting of chromium 2, and ruthenium 3, right? So see here, we have sigma star to sigma star in this first one. Wait a second. Chromium 2. Yeah. So this I have considered first as chromium 2 and cobalt 3, right? You can see here. Cobalt 3, cobalt is in the plus 3 oxidation state here, and chromium is in the plus 2 oxidation state, right? You can see chromium in plus 2 oxidation state and cobalt is in plus 3. Okay. So as cobalt is in plus 3 oxidation state, yesterday also I mentioned this, that except with the few ligands like the halide ions, Bn3 minus, S2 minus, SCN minus, leaving those ligands, with every other ligand, the cobalt 3 behaves, the cobalt 3 is low spin, right? The meaning the spin paired, the electrons will remain paired. So that is why it is a D6. So D6 that will involve a T2G6 and EG0. All the electrons will remain paired in the T2G. Okay, and for the chromium 2 plus, it is chromium 2 plus D4, right? Chromium 2 plus will be D4. This will be your high spin complex, right? So T2G3 and EG1, right? 3 electrons in T2G and 1 in EG. So now see how electron transfer is taking place. From EG of this complex, chromium, EG of this chromium, EG of this chromium, chromium is in the plus 2 oxidation state. It is transferring electrons to the EG of cobalt 3 plus, right? Because it is in the higher oxidation state. It is in need of electrons. Now this mechanism is very important in other aspects also. So you can see in detail here. This mechanism I've shown in detail. So this is one complex of cobalt 3 plus and this is your chromium 2 plus, right? On adding 5H3O plus, the uh, on adding 5H3O plus, we get this complex chromium in the plus 3 oxidation state and cobalt in the plus 2 oxidation state. Okay, so these are basically redox reactions. The electron transfer is taking place. So this is an example of inner sphere mechanism. Okay, inner sphere. How? You can see that this Cl is acting as a bridge. I mentioned there that in the inner sphere, bridging ligand is present, right? So you can see here that cobalt NH3 5Cl2 plus D6 low spin. I have shown it here, inert. This is inert. Yeah, inert. Why inert? Because T2 these electrons are filled in the T2G, right? These are present in the T2G. They are not present in the EG. So this is inert and this one is labile, and there it is a condition for the inner cell mechanism that one of the complexes has to be inert and the other has to be labile. So this one is labile, right? So the electron transfer takes place from EG of this complex to the EG of this. You can see it here that the chromium 2 plus, chromium is in the plus 2 oxidation state. It will transfer the electrons to Cl and this Cl will transfer the electrons to cobalt. You can see that halide ions are polarizable and attract the electron density from chromium 2 plus. So they attract the electron density from chromium 2 plus. You can have fluoride ion also or iodide also. And if iodide is present, I minus is present, when I minus is present, then in that case the rate will be very high. Okay. Why? Because it is polarizable, it has a large size. It will be able to attract electron density from chromium very, very, like in a very well manner. Okay. So now after the transfer, the chromium has become plus 3 and cobalt has become plus 2. Right? Now this has become inert and D3 and this has become labile, D7. Okay. It will be having electron in the EG, this cobalt 2 plus. Now what happens is, now CO of cobalt, this complex is formed, cobalt in with 5NH3 and the Cl is transferred to this chromium, right? This complex, it has become inert and this is labile, right? So on adding H2, on adding water, what will happen? You can see on adding water, it will take up one water molecule and it will become in the coordination number 6. Coordination number will be 6 here for the cobalt. I'll write it. And on rapid hydrolysis, what do we get is all these ligands, the NH3 5, are replaced by water, and we get this complex, right? Cobalt in the +2 oxidation state, and 5NH4 plus are released. Okay. So this mechanism is very important. You have to see it carefully, how the transfer is taking place. Yeah. So I have shown it that the Eg to Eg, here it is inner sphere, right? This one is inner sphere. Now if we talk about the first one, it is chromium 2 and ruthenium 3. The chromium 2 and ruthenium 3. Now you can see here. See, chromium is in the +2 oxidation state here, D4. Low, it will be high spin. Water is a weak field ligand, T2G3, Eg1. Okay. So this will be the HOMO. The electrons will be transferred from the HOMO to the LUMO. As in organic chemistry we study, the highest occupied molecular orbital, the electrons are transferred from HOMO to LUMO, right? So, and then this ruthenium 3 plus. So you have to see here that ruthenium is there. Now if you go from 3D to 4D to 5D, right? For the 4D and the 5D, uh, whatsoever is the ligand, whether it is weak or it is strong, it will be a low spin complex. It will form a low spin complex only, okay? Because the splitting, the delta naught is very high for these 4D and 5D, okay? That is why. So ruthenium will be in the +3 oxidation state, and this will be D5. Iron, ruthenium, osmium, right? 3D6, 4s2, 3 electrons have been removed, and we get D5. Okay, so this will be low spin. This will be low spin, but it will be low spin only, whatsoever is a ligand. So low spin T2G5, Eg0. All the electrons are present in the T2G, right? And now this has, because now you can see here that for the T2G, right? 5 electrons are there. Okay, 5 electrons are there, and one more electron can be filled in this T2G, right? So this will be the LUMO and not Eg. So this will act as a LUMO, and the Eg will be HOMO. So electron transfer is taking place from Eg to T2G, right? Sigma star, which is your Eg, and T2G is your pi star. So the rate of acceleration in going from outer sphere to an inner sphere mechanism is lower for 1 relative to 2, because the HOMO and the LUMO are sigma star and pi star respectively. You can see the HOMO and LUMO are, HOMO is this sigma star and pi star, LUMO is pi star. That is why. Okay, inner sphere mechanism is faster in comparison to the outer sphere mechanism. Okay, you have to see this, that the Eg to Eg transfer, it is faster. Okay, the Eg to Eg transfer is faster as compared to the the Eg to T2G. Okay, the inner sphere is faster as compared to the outer sphere because a bridging ligand is present, so it will facilitate the electron transfer. So that is why the option B is correct. HOMO and LUMO are sigma star and pi star respectively. So that is why the rate of acceleration going from outer sphere to inner sphere is lower for one relative to two, because of HOMO and LUMO are sigma star and pi star. The rate is 10 times greater here for the sigma star to sigma star transition than this one. Okay, 10 times, 10 to the power 10 it is. It is 10 to the power 10 here for the this one. Okay, so this one is done now. Okay, if we see the next question. Yeah. The metal ion which is most likely to show the low spin high spin equilibria in its complexes has the electronic configuration. Okay. So low spin high spin equilibria in its complexes. So these are the configurations that have been given. So you have to see that high spin low spin equilibria is shown only by D6 complexes. Okay, only the D6 complexes show the low spin high spin equilibria. So this is one example of the low spin high spin equilibria. where iron is in the plus 2 oxidation state. Okay, so plus 2 oxidation state, that means 3d6 4s2, 2 electrons have been removed and we get the 3d6 configuration. Okay, so this is important, you have to see this. At a temperature greater than 174 Kelvin, it exists as a high spin, while at a temperature lower than 174 Kelvin, then it exists as low spin. Okay. At lower temperature, energy of the electrons decreases and hence they remain paired. Okay, hence they remain paired, and it will be a low spin. This is another example, diphenyl terpyridyl, where three pyridine groups are attached from the ortho position, right? From the ortho position, diphenyl terpyridyl, low spin below 300 to 323 Kelvin and high spin above this range, right? This complex, the iron diphenyl terpyridyl. Okay, so you can see this also, that when the CFSC becomes comparable to the pairing energy, when the CFSC when the CFSC becomes comparable to the pairing energy, then spin crossover, high spin, low spin equilibrium occurs. Okay, so in these cases, the iron diphenyl NCH2 and in this phenyl diphenyl iron diphenyl terpyridyl 2, the CFSC becomes comparable to the pairing energy, and then this spin crossover, high spin, low spin equilibrium occurs. Okay, so it is an example of D6. Okay. Now we move on to the next question. Yeah, this is also very important, water exchange. In GATE, such kind of questions are asked. The water exchange. Arrange the following metal ions in the increasing order of their water exchange. So these are the metal ions that are given: vanadium 2 plus, nickel 2 plus, iron 2 plus, manganese 2 plus, and copper 2 plus, right? So the rate of water exchange depends upon the charge density, charge by size ratio. Okay. Um, smaller the size, smaller size ions will not allow the water exchange easily. That we'll see here. You can see that vanadium 2 plus has a configuration of D3 leading to inertness. Now you can see that vanadium 2 plus, if we draw it like this here, vanadium 2 plus, okay, scandium, titanium, vanadium, right? So 3d3, 4s2, vanadium. So, and if we remove two electrons, it is d3. It becomes d3, right? So three electrons are present here. According to VBT, we are seeing valence bond here. Okay. Now, and here it will be S, 3d, 4s, 4p, d2, sp, right? Now you can see, yeah. So yeah, this one is there. So this is D3. Vanadium 2 plus is D3, right? Now you can read it. According to VBT, inner sphere orbital complexes are inert, while outer orbital complexes are labile. So what are the inner orbital complexes? They are D2sp3, right? They use the inner D, that is 3D, 4s, 4p. And what are the outer orbital? The outer orbital is 4s, 4p, 4d. The outer D is used, right? So they are labile, according to VBT. So a labile complex should contain a low line vacant orbital. No, so also what do you mean by low line vacant orbital here? Now, if you talk about vanadium in the plus 3 oxidation state, so vanadium in the plus 3 oxidation state will be 3d3, 4s2 is the 4s2, 3d3 is the configuration, right? And if we remove 3 electrons, we'll get D2, right? I'll just show it in this itself. So, no. First you see this one, vanadium in the plus 3 oxidation state, get it, right? Only 2 electrons will be there, right? For the vanadium 3 plus, D2. Only two electrons will be there, and this orbit, I'll rather draw it like this. Okay. So 1 and 2. Yeah. So for the vanadium 3 plus 4s2 3d3, three electrons have been removed, we get this. So this you can see this orbital, this is empty, right? This one is empty, this orbital. So this is called a empty low-lying vacant orbital. This is empty. This is what it is a low-lying vacant orbital. Okay. So in the case of vanadium 2 plus, here I'm talking about here, which is given in the question, vanadium 2 plus, it will be 3d3, right? This is 3d, 3d, and this is 4s, and this one is 4p, right? Yeah. So in the case of vanadium 2 plus, there is no low-lying empty vacant orbital and forms inner orbital complexes. You can see here that this orbital is not empty here. We have three electrons present, 1, 2, 3. These are empty. One. So the configuration, what is the hybridization that becomes is D2sp3, right? This is D2, D2s, and T3. So according to VBT, the inner orbital complexes, that is the D2sp3, it is inert. So that is why this V2 plus is inert, definitely. So it is at the last, V2 plus, right? Now talking about these three, nickel, iron, and manganese. Now you can see in going from left to right, the size is decreasing, right? So manganese has the highest size, then iron, and then nickel, right? The size. If we go from left to right, the size is decreasing, and size is in this order: manganese, iron, and nickel. Now the rate of water exchange depends upon the charge density. So greater will be the size, lesser will the it is inverse relation like water exchange. So nickel has a small size. It will, I've written it here, nickel 2 plus will make a strong bond with water, and hence the water exchange decreases because it has a small size. And then iron, which is shown here, iron, and then manganese. Manganese has a large size. So it can easily exchange the water ligand with the other ligands, right? Now, talking about this water, Jahn-Teller distortion. This is important. You cannot miss this topic. So for the case of copper 2 plus, due to Jahn-Teller distortion, it has highest tendency of water exchange. So if I talk about the Jahn-Teller distortion, so the copper 2 plus, right? Copper 2 plus is D9 configuration, right? D9. So you would have seen that in the D9 complexes, a tetragonal, yesterday also we had seen about the JTD, that the tetragonal elongation and tetragonal compression is present for the when JTD takes place. So what happens in tetragonal elongation is that the dz square. Now we know that it has, it is like this. Uh, it is arrange the following method. arrange the following metal ions in the increasing order of their water exchange. So the rate of water exchange depends upon the charge density. So we have discussed about the vanadium 2 plus, right? And we have discussed about the size also. So coming to the Jan-Teller distortion, what I was saying that we know that it is T2G and EG, dxy, yz, and xz. This is this. And the higher orbitals are dz square and dx square minus y square. So what happens in tetragonal, this is dx square and dx square minus y square. So what happens in tetragonal elongation, if I talk about that, the the dz square energy is lowered and dx square minus y square energy is increased, right? So why the dz square energy is lowered? You can see that two electrons are present. I'll just draw it. That talking about D9, right? So uh, here the electrons have been filled. Electrons are present here, right? 6 electrons are present here. Here there are 3 electrons. So this one, the lower one is dz square and the higher one is dx square minus y square, right? The higher one is dx square minus y square. The energy of dz square is lowered as it has more electron density. It will be able to repel the ligand electrons more, and hence its energy is lowered. While the this one, the dx square minus y square, the higher one, it has less electron density and it will be able to attract the electron density of the ligand, right? So that is why there will be a repulsion also. So that is why the energy is high for the dx square minus y square. And now if we the dz square in the tetragonal elongation, you can see that the two bonds become weak, the along the axis like the dz square. And for the case of tetragonal compression, four bonds become weak, right? Along the dx square minus y square, right? Along that. So that is about the JTD, Jan-Teller distortion. So the bonds become weak basically in the tetragonal. The octahedral complexes experience Jan-Teller distortion. Okay. So that is why the bonds become weak and it has a highest tendency for water exchange. So they can exchange the water ligands easily, right? Okay. So talking about the next question. Okay, so we have to find the magnetic moment. So magnetic moment is also very important for the chromium, for the exam. Mu calculated for chromium 2 plus complex in high spin and low spin complexes would be. So high spin, the configuration is 4s1, 3d5, and if we remove 2 electrons, it will be d4, and low spin also it is chromium 2 plus d4. But the arrangement will be different here. You can see that the magnetic moment is calculated using the formula mu, which is your magnetic moment, and it has a unit of Bohr magnetism, root under n plus 2, where n is the number of unpaired electrons that are present in the T2G and EG orbitals, right? So for the high spin chromium 2 plus, the configuration is T2G3 and EG1, right? For the high spin. How? High, 1, 2, 3, 3 in the T2G, 1 electron goes to the EG. Why? High spin. It is high spin, right? You can see high spin. 4 unpaired electrons will be there. So 4 plus 2, whole under root, that will be 4.9 Bohr magneton. Now, if we talk about for the low spin chromium 2 plus, the electrons will remain paired as it is low spin. The configuration is T2G4 EG0, right? All the electrons, T2G will have 3 electrons will first fill singly and one more electron will go itself in the T2G. So 2 unpaired electrons will be there for this one, T2G4, right? 2 unpaired electrons will be there. You can see here that this is your T2G. 1 electron is present. T2G4, right? Two unpaired electrons are there. So these two are other unpaired electrons. So if we calculate the magnetic moment, root under 2 plus 2, that will be 2.83, right? So the answer will be 4.9 Bohr magneton and 2.83 Bohr magneton respectively for the high spin and the low spin complexes. The formulae of the magnetic moment, like there are other formulas also, they are very important because every year question is asked from this topic, magnetic moment. Uh, for the lanthanides also, lanthanides and actinides. Okay, so yeah, mm, this is all for this question. Yeah. So moving on to this question. Yeah, this is another for titanium H2O6 3 plus. The absorption maximum due to DD transition is found at 20,000 centimeter inverse. Okay, so the absorption maximum is basically your delta naught only. You need to understand the language of the question. That is very important. That is why practicing questions is important. In general questions and the previous year questions, everything. Okay, so anyway, the absorption maximum due to DD transition is found at 20,000. Therefore, the crystal field stabilization energy is, now you have to find the crystal field stabilization energy. So titanium is in the +3 oxidation state. You can see here titanium, so scandium, titanium, 4s2, 3d2. Removing the 3 electrons, only 1 electron is present. So the configuration becomes D1, T2G1, EG0, right? And delta naught is given as 20,000. Here only it is given the absorption maximum, that is your delta naught, the difference between the T2G and EG, that is given to us. So for calculating the CFC, the formula we'll use, yesterday also we had seen this, minus zero point 0.4 into 1 plus 0.6 into 0. So multiplied by 20,000, this is what we get, minus 8,000, right? Okay. So this is what we get. So D will be your correct option. Okay. Yeah. Now this is another for the spinal part. Okay. Now inverse spinal. This spinal is given to us. We have to find that which is it, inverse, normal, or mixed. Okay. NiCr2O4. Yesterday only I had told you about the spinals, right? When we have the formula AB2O4, right? AB2O4, AB2O4. This oxygen is present in the lattice points and A and B are present in the voids, right? When A is present in the tetrahedral void and B is present in the octahedral void, we call it a normal spinel. So this is your +2 oxidation state. A is in the +2 oxidation state and B is in the +3 oxidation state, right? And when do we call it an inverse spinel? When one of, we have 2B, right? 1B goes to the tetrahedral void and this A goes to the octahedral void. Like we'll be having A, B, and B, that will be there, right? So 1B enters the tetrahedral void, B3 plus, and this A2 plus and B3 plus go in the octahedral void. Then it will be a inverse spinel, right? Okay, so that is not required. That is just for your information. Because it is not required in this question, but you should know this, that where the ion is present in the tetrahedral void or the octahedral, because questions based on that is also like they can also ask such questions. So calculating the CFSC in the octahedral field, you have to find the CFSC in the octahedral field for the nickel 2 plus, right? I told you AB2O4, A is in the +2 oxidation state, B is in the +3 oxidation state, right? So nickel is A, chromium is B. So nickel 2 plus is T2G6 Eg2, right? 3D8, 4s2 3D8, 2 electrons have been removed, we get 3d8, T2g6, Eg2. So 6 electrons are here, 6 into minus 4 plus 2 into zero point 0.6, 2 into zero point 0.6 delta naught. So this is what we get. And for the chromium 3 plus, you can see here that chromium 3 plus will be 4s1, 3d5, and it will be 3d3, right? After the removal of 3 electrons, it will be 3d3, T2g3, and Eg0. So 3 into minus zero point 0.4 plus 0 into your zero point 0.6 that I have not written, that is not required, delta naught. So that now you can see that here this question is important. That is why I have included this one. The CFSC is same. Now in that case, what you will do? I told you when the CFSC of B is greater than A, then you will see that it is a normal spinel. Now what you will do when the CFSC is same? Now you can see the calculated CFSC is same for both the ions, nickel 2 plus chromium 3 plus. The differentiating factor is the charge. The charge, yeah. So chromium 3 plus has a higher charge than the nickel 2 plus, right? Higher the charge, greater will be the value of CFSC, delta naught. So there will be some contribution because of this charge also. So the CFSC will increase in this case because the charge is high. Yeah, so it will be able to attract the electrons from this O2 minus, which is in the lattice points, towards itself more because it is electron deficient. It has a higher charge, and splitting will increase. The CFSC, right? Delta naught will is increase. So hence it is a normal spinel. Why? Because B3 plus is greater than A2 plus, the CFSC. So chromium 3 plus is greater than nickel 2 plus, right? So this is the reason. This is your normal spinel. Okay. Now moving on to the next question. Yeah. So this question is also relevant for the chemical bonding part also, but as we see the lattice energy trend in this chapter as well, so you can include it here also. So assign the order of lattice energy to the following ionic compounds: cesium fluoride, sodium fluoride, potassium fluoride, and lithium fluoride. So we know that these all of these ions, the cations, belong to one group: lithium, sodium, potassium, rubidium, and cesium, right? So when one mole of an ionic compound is formed from its constituent gaseous ions, some amount of energy is released. This is known as the lattice energy. Okay, this is the definition of the lattice energy. So we know that down the group, size of the metal is increasing. I'm talking about the cation because an ion is same in all these cases, fluoride, right? So I'm talking about the cation. The down the group, size of the metal increases. That you know this fact. Uh, and also, you can see it here. I've written the formula for the lattice energy. Lattice energy is minus n a z plus z minus by r naught into 1 minus 1 by n. So what is n? N is Avogadro's number, 6.022 into 10 to the power 23 per mole, right? This is n. A is your Madelung constant, depends on the geometry of the complex, or sorry, the ionic compound. R naught is your interionic distance, distance between the two ions, the cations and the anions, and n is your Born exponent, right? Now you can see that there is an inverse relation between the lattice energy and the interionic distance. It is mentioned here. Lattice energy is inversely proportional to 1 by, like it is proportional to 1 by R naught, right? So with the increase in the size of the metal, interionic distance also increases. Okay. So as R naught is increasing, the lattice energy will decrease. So that is why the order of lattice energy becomes lithium, highest lithium fluoride, which is greater than sodium fluoride, potassium fluoride, and cesium fluoride. Cesium has the highest charge. So interionic distance will be highest, and lattice energy will be least for this ionic compound. Okay, so this is the order. You can see order of the lattice energy. So that is what it was asked in the question. Assign the order of lattice energy. Okay, so we are done with this question. This is also important. You need to understand this. Okay. So the light pink color of cobalt H2O6 2 plus and the deep blue color of COCl4 2 minus are due to. You have to answer it why the color is this way for these two complexes. So these are the options that are given. You can read it. MLCT transitions and DD transitions. LMCT, this is metal to ligand charge transfer, ligand to metal charge transfer, DD transitions. DD transitions in the first, metal to ligand charge transfer in the second. You can see that metal to ligand charge transfer occurs when there are pi acceptor ligands present, right? You have to see that from the metal to the pi star of the ligand, the electrons are transferred. So this cannot be the answer because there is no pi acceptor ligand present. For example, Cn is there, Co is there, they are pi acceptors. So it is not here. So we can cancel this out. This MLCT transition is not possible in the first. So you can cancel this out on the basis of this only, MLCT, right? And no need to see this one. And after this, you can see on the basis of MLCT only. Okay, so moving on to the next part, it is LMCT transition in both ligand to metal charge transfer. So the ligand to metal charge transfer occurs when the metal is electron deficient, right? Metal is electron deficient. So, for example, in the case of so that kind of ions are also not present here. So you can eliminate this option as well, right? You can eliminate the options and answer. So now we can see this one. Again, MLCT is there. You can see that metal to ligand charge transfer pi acceptor. The pi acceptor ligand should be present, metal to ligand charge transfer. So pi acceptor, so that the electrons can be donated from the d orbital of the metal to the pi star of the ligand. Okay. So that is also not present. Pi acceptor ligands are not present. Cl4, Cl is a pi donor. It is not a pi acceptor. Also, H2 is a sigma donor. It is also not a pi acceptor. So you can cancel out this option as well, right? Only this option is left. Even if you don't know the answer of this question, and you know only about MLCT and LMCT, you can eliminate the options and answer. Okay, you have seen that. Even if you don't know about DD transitions, it is fine. But however, we have to see it because it can be asked in some other way as well. Okay. So you can see here both the complexes have spin allowed transitions as delta S is 0. Now you have to see what is spin allowed. Okay. Now cobalt in the plus 2 oxidation state 3d7, 4s2, 3d7, 2 electrons have been removed, 3d7, octahedral. So we have filled the electrons. Water is present. In both the cases, it is weak field only. So you'll fill it like this 1, 2, 3, 4, 5, 6, 7. Right? Spin is 3 by 2. 3 unpaired electrons are present. Spin is 3 by 2. And after transferring one electron as it is to this orbital on giving energy, it will be here. The spin has also been not has not been changed. You can see here. It is here now. Now also it is 3 by 2. 3 electrons are unpaired, right? So S2 minus S1, if you do 3 by 2 minus 3 by 2, it will be 0. So it is spin allowed. That means delta S is 0, right? So this is spin allowed. Now if we talk about the tetrahedral complex, okay, it is CO2 plus 3D7 is there. So how you will fill it? This is a tetrahedral. So Eg will be below and T2G will be high because the ligands are not directly approaching and they are in between. You know about the tetrahedral structure, right? The ligands are approaching from between and not along the axis directly. That is why Eg is below the dz square and dx square minus y square, and the T2G is high. Dxz, yz, xy. Okay. So 1, 2, 3, 4, 5, 6, 7. Now also three unpaired electrons are there. So half plus half and plus half. It will be 3 by 2. And on given energy, one electron is transferred here. As it is transferred. Now also the spin is 3 by 2. Half plus half plus half, right? So if S2 minus S1 if we do, it will be spin allowed. Delta S is 0 here. So in both the complexes, spin allowed is there. Spin allowed transitions are there for both the complexes, this tetrahedral and this octahedral complex. Okay, why I'm saying tetrahedral? Because Cl is a weak field ligand. Okay, Now, this is important. Laporte selection rule, delta L is plus minus 1, where L is the orbital angular momentum quantum number, right? L is your orbital angular momentum quantum number. So GU, what is this G? G is basically like, now if you talk about, supposedly if you talk about I'll show it. Now if we talk about the octahedral complex, for example, okay. So if we consider this middle point, this point, okay. Now on moving from here to here, you are getting like, for example, if we take up a simple example, like H2 is there, right? And HCl is there, right? Leave this octahedral. I'll explain you simply in a very normal manner. Like, okay, this is H2, and on moving from this point to here, you are getting H, right? And from here to here, you are getting again H. So this is G rate. This is what we call G rate. It has a center of symmetry, right? Center of symmetry is there. You are getting H, and you are getting H here as well. And for this one, you are moving here, you get H, and you're moving here, you're getting CH. So there is no center of symmetry, center of inversion is not present. Center of symmetry or center of inversion is the same thing. So you're moving H, you're getting LCL. It is not present. So this is what? This is U, right? Unjared. So that is, this is what we talk about in terms of your p orbital and s orbital. S orbital, the electron density is present all over, so we can say it is Jared. And for the p orbital, it is unjared. Okay. P orbital, you can see that plus and minus is there, right? So G to U is allowed. Like if we talk about S to P, F is Jared, P is unjared. So Jared to unjared is allowed, while Jared to Jared, if you talk about DD, D is Jared and D orbital is Jared, right? If we talk, see, I'll show you here. Now, wait a second, I'll show it here. So if we talk about this orbital, right? Suppose this is this is dx square minus y square orbit. Here it is plus. Here also it is plus. So on moving from this point to here to here, and this point to here, it is same. And similarly from here to on the y-axis, this is your y-axis, and this is your x-axis, right? On moving from plus to plus, so it has a center of symmetry, dx square minus y square. So that is why it is G rate, right? So D orbital is G rate. So G rate to G rate and unjared to unjared are orbital. You have to see. Okay. So D, which is L, is 2. You know that the orbital angular momentum quantum number, L is 0 for S, it is 1 for P, it is 2 for D. Orbital is G rate, right? So DD transitions are Laporte orbital as delta L becomes 0, right? Delta L becomes 0 because it will be Jared to Jared. The s orbital is Jared, the p orbital is unjared, d orbital is again Jared, f orbital is unjared. You have to understand about this center of inversion concept. Then on that basis you have to we can say that it is Jared or unjared, right? So DD transitions are Laporte orbital as delta L becomes 0. It will be a Jared to Jared. So due to this reason, the given octahedral complex appears light pink in color. The color is light. And the epsilon value, the molar extinction coefficient that we talk about in the absorbance term, absorbance is equal to epsilon Cl, right? So the epsilon value will be low for this complex, cobalt H2O6. Now, if you see here, yeah, some relaxation in the Laporte selection rule is seen for the tetrahedral complexes, that's COCl42 minus complex. As the tetrahedral complexes have no inversion center, you know that, right? It has no inversion center. Now, if we talk about CH4, for example, or any other tetrahedral complex you can take, Tetrahedral has no inversion center. Wedge is, you know about this wedge and dash, right? Wedge is coming towards you and this dash is going away from you. So if we consider a central point here, on going from here to here, we are getting a point. This is in space. You cannot say that on going from here to you are getting. Here it is nothing, but here you are getting something, right? The tetrahedral, actually, I'm not able to show it here. So, well, as the tetrahedral complexes have no inversion center and involve PD mixing. So, PD mixing, so it is not pure D now. PD mixing comes from the MOT theory. The the P and the D mix to form a T2, right? T2 of the metal and the T2 of the ligand. They mix. They on that basis, the MOT is formed, the molecular orbital diagram. Okay, between of the tetrahedral complexes. So as the tetrahedral complexes have no inversion center and involve PD mixing, the Laporte rule becomes partly allowed for them because it is not pure D now and P has also come into play. That is why the Laporte rule is relaxed in the case of tetrahedral complexes, and thus the given tetrahedral complex appears deep blue in color because the Laporte is partly allowed here while the Laporte is forbidden in the case of DD, the octahedral. Okay, so this is your answer C, DD transitions in both. However, PV transitions are occurring here also, but they are weak, they are forbidden only. You can see it is forbidden only. That is why light pink color is there, and it is not forbidden. It is partly allowed. Laporte is partly allowed for this one, even though this is also DD, but partly allowed for the tetrahedral complex. That is why PV transitions. Okay. Yeah. So the next question is the rate of substitution of Cn minus by 14 Cn minus is higher for which of the following complexes? Now this is a case of a substitution reaction. This is also very important. Associative mechanism and dissociative mechanism. The octahedral complexes follow the dissociative mechanism. The square planar complexes follow the associative mechanism. Okay, you can see that this is a square planar complex. I told you yesterday that nickel is in the +2 oxidation state, Cn minus, strong field ligand, D8, it will be a square planar complex, right? And this is the octahedral complex, you can see. Now, you can the K1 and K2 are the rate constants. The complexes of coordination number 4 undergo substitution more rapidly. This is coordination number 4. You can see here. This is the square planar. I have just taken general one, MLL, rather than this complex, but it is the same. The complexes of coordination number 4 undergo substitution more rapidly since there is enough room around the metal cation for entry of the incoming ligand, right? Space is there. You can see in between there is a lot of space here, right? The fifth ligand enhances the rate of removal of one of the 4 ligands already present, right? Now, if you add a nucleophile to it can come here. Now there will be a repulsion and it will facilitate the removal of one of these. Any of these can go. So it will be this will be a substituted complex, right? So one is square planar and 2 is octahedral. But the substitution in octahedral, it is like it has to go through the dissociative mechanism because already there are 6 ligands present, and one more ligand, entry of one more ligand will create a lot of steric hindrance. So because of that reason, the rate is lowered for this one, the octahedral, as compared to the square planar, right? So the rate of square planar K1 is higher than K2, order of rate of substitution by substitution of Cn minus by 14 Cn. This is the isotope, okay, labeled. Yeah, yeah. So you can see here if the square planar complex, if we add 14 Cn minus, K1 is the rate constant. So one of the Cn will go and this will be replaced by 14 Cn, right? And here if you see, this is the octahedral complex, 14 Cn minus is added, K2, the rate constant, and this is what we get, Cn5 and 14 Cn. One of the Cn has left, right? Okay. Yeah. So this is another question. The crystal field splitting energy for COCl6 4 minus is 18,000 centimeter inverse. This is the octahedral complex, right? This is a simple question. Um, the delta, it is not given delta O or delta T. You have to find it yourself, right? That you should know. The delta for COCl4 2 minus would be, this is a tetrahedral complex, weak field ligand, this is octahedral. Now this is a formula. This formula you have to remember, okay? You have to remember this, that the delta for the square planar complexes, you can remember the square planar is greater than delta for the octahedral, which is greater than delta for, this delta is CFSC. CFSC, yeah, the difference between the T2G and EG tetrahedral, right? Yeah. So this is the trend of CFSC. So anyway, delta T, CFSC of the tetrahedral complex, and del O, CFSC of the octahedral complex. Delta T is 4 by 9 of 18,000. 18,000 is given to us. Crystal field fitting energy delta for COCl6. This is the octahedral complex. It is 18,000. You can see it. 18,000 into 4 by 9. It will be 8,000, right? So this is your C is your correct option. Okay. So delta T, crystal field stabilization energy for the tetrahedral complex, this one, COCl4 2 minus, would be 8,000, right? Yeah. So that's it.